Hi everyone, myself Dr. M. Lakshmi Prasad, working as a professor in the Department of Computer Science and Engineering in Institute of Aeronautical Engineering, Hyderabad. So in this video, I'm going to discuss about graph data structure. So graph is a nonlinear data structure, which consists of vertices or nodes, and which is going to be connected by edges or arcs. So where the edges may be directed and directed. So the graphs are powerful and versatile data structure, so that easily allow to represent the real life relationships between the different types of data. So there are two main parts of the graph. So like vertices where the data is stored, and edges, connections which connect the nodes here. So the vertices I and j are adjacent. So if and only if I and j is the edge in the graph. So a nonlinear data structure consists of vertices or nodes connected by edges, where the edges may be directed or undirected. And graphs are powerful and versatile data structure that easily allow to represent the real life relationships between different types of nodes. And vertices I and j are adjacent vertices if and only if is an edge in the graph. So graphs and its representation. So the choice of graph representation is said that it should be a situation specific. So mainly we are going to be follow two types of representations here. So first one adjacency matrix and second one is adjacency list. So these are the two types of conventions used for representing the graph here. So the graph is said to be a situation, so mainly depend upon the operation that are going to be performed and easy of use. So for that purpose, this representation should be helpful. So the first one is that adjacency matrix. So it is a 2D array of size v by v. So where v should be the number of vertices in the graph, and so let the 2D be an array. So represented as adjacency matrix and should be 1. I'm going to assign the value 1 whenever there is an edge from vertex I to vertex j. So between the pair of vertices, the cost of edge also is stored, and this shows that which vertices are adjacent to one another. And for undirected graph of the graph is repeated information, hence the matrix are said to be space insufficient. So the memory of use of adjacency matrix is represented as equal estimate of n square. So where n should be the number of vertices. So adjacency matrix. So this is the 2 by 2 matrix. Should be of the size v by v, where v should be the number of vertices in the graph, and for each pair of vertices, so a cost of an edge is also going to be stored. So for undirected graph, so the matrix should be space inefficient, and at the same time it is going to be a big size of big O estimate of n square, where n should be the number of vertices. So what are the advantages of this adjacency matrix is that so it should be easy to understand and implement and then convenient to work with, and it should be removing an edge, so involves the time complexity of big O estimate of 1, and queries like where there is an edge from vertex u to v are efficient and require the time complexity of big O estimate of 1. So if I'm going to consider a graph here, so this graph is going to be represented in the form of set of vertices 0, 1, 2, 3, 4. So in these vertices, so what I'm going to say, so if I'm going to consider the vertices and along the rows and then columns, so in this one, so if there is an edge from one vertex to another vertex, I'm going to represent 1, otherwise I'm going to represent it as 0. So from 0 to 0 there is no edge actually, so that's why I'm going to represent 0 here. So if there is an edge from 0 to 1, so I'm representing 1, and similarly I have edge from 0 to 4, so I'm representing 1, so remaining or should be 0. Similarly, if I'm going to consider 1, so if 1, so I have edge from 1 to 0, so 1, and 1 to 2 I'm having edge 1, and 1 to 3 also I'm having an edge, and 1 to 4 also I'm going to have edge, so remaining should be 0. And if I'm going to consider 2, so what will happen? So I have an edge from 2 to 1, so 2 to 3, so only from 2 to 1 and 2 to 3 I'm going to have to make it as 1. So what are the disadvantages of this one? So the main disadvantage is that it should be consumes more space. It should be of the size equal estimate of v power 2. Even if the graph is a space containing less number of edges, it consumes this same space. And if the same number of nodes in the graph may change, so then it should be represented as maximum size of the graph. An adjacency list. So in this representation, every vertex of the graph contains a list of adjacent vertices. So the advantages of using this adjacency list as follows. So the addition of vertex and connecting new vertices with the existing one should be the easier, and should have the space complexity equal estimate of mod b plus mod e, and it allows to store the graph in more impact form and get the list of adjacent vertices, which is the big benefit from the many algorithms. So the adjacency list of is going to be presented as following advantages. So the time complexity, the space complexity is less when compared to the adjacency matrix, and it allows to store the graph in more compact form, and it should be the big benefit for the many algorithms. When it comes to disadvantages, so here the disadvantage is that whenever there is an edge from U to V are not going to be efficient and require the time complexity also, and it does not allow to make the efficient implementation, and if the dynamic change of vertices is vertex number is going to be required. So the main disadvantage of this adjacency list is that, so whenever there is an edge from U to V are not efficient and then require the time complexity of V also, and it does not allow to make an efficient implementation if the dynamic changes of vertices number is required. And types of graphs, so we are going to have different types of graphs like undirected graph, directed graph, and weighted graph. So what is undirected graph means that, so all the edges are undirected if the connection is symmetric, and then we can able to say that there should be undirected one. Directed graph means all the edges are directed, and if there is an edge implies one direction of connection, we say that the graph is directed. And weighted graph is the graph where each edge is going to have associated numerical value, what we call it as weight here. So undirected graph looks like this, where the edge does not have any kind of arrows, whereas undirected graph I'm going to have directions here, and weighted graph means where I can able to assign some values here, so that should be weighted undirected graph. Similarly, if I'm going to assign the edges in directed graph also, then it should be have directed weighted graph. So undirected graph, so a pair of vertices representing any edge in an unordered, so the pair UV and VU represent the same edge. So example, if I'm going to consider the graph here, so this vertices of the graph will be 0, 1, 2, 3, 4, and edges 0, 1, 0, 2, 1, 3, 1, 4, 2, 5, and then 2, 6. So G2 also a tree that is a special case of the graph, and should be called as a tree. And so undirected graph is said to be connected if there is a path between every pair of vertices in the graph. So directed graph, so here The edge is represented by ordered pairs. So example, a graph G3. So the set of vertices will be 0, 1, 2, and edges will be 0, 1, 1, 2, and then 1, 1, 0, and then 1, 2. So a directed graph is the directed path is the directed graph is the sequence of distant vertices such that there is an edge from each vertex in the sequence to the next. And weighted graph. So weighted graph is the graph where each edge has an associated numerical value called weight, and this weighted graph should be either directed or undirected, and the weight of the graph is often referred to as cost of the edge. So example, so in this graph the cost of the edge is 5, so here is 3 and this 4. So these are not called weights, and this should be called as edges, and this one called as vertices. Some of the graph traversals what we are going to have is that BFS and then DFS. So traversing means visiting all the nodes of the graph exactly once. So if you want to visit every vertex and every edge exactly in some well-defined order, so for that we need two types of algorithms. So depth first search and then breadth first search. So in depth first search and breadth first search, so first of all you have to visit the node and you have to be put n children in a list either in a stack or queue data structure, and for each child in the list you have to search that node. So if I am going to use a stack then recursive, then you can able to get DFS. If I'm going to use queue data structure, then I can able to get breadth first search. So stack is the concept of linear data structure. So where it should be a data structure where the insertion and deletion takes place at one end only. So this deletion operation called as push, and for deletion of insertion operation called as push, and deletion operation called as pop function. So we're able to insert the elements and delete the elements only one end. So this end should be closed. And Q is a linear data structure. So in which the insertion and deletion takes place at two ends, what we called as front end and then rear end. So in front end, we are going to be delete the items, and rear end we are going to be insert the items. So whoever comes first into the queue then goes out first. So this queue follows first in first out principle. So whereas this stack follows last in first out principle. So depth first search. So visiting all the children before the first grandchild. So the visiting order is that first we have to visit the vertex, then visit all its neighbors, and BFS should be the best finding the shortest path in the graph, and needs flags or some way to prevent the infinite loops as well. That should be becomes the weakness in that BFS. So the BSOS algorithm, if I'm going to take it, so create a queue. So mark B is visited and put that B into the queue. So until the queue is empty, so remove the head of the queue and mark all the end queue of all unvisited neighbors of the queue. So example, so this is the algorithm, this is the problem we're having. So for this I need to find the BFS order of this graph. So in this one, the first I'm going to be visit the root node. So that is the A. So after that, I'm going to be after this I'm going to visit the next node. So which I can able to visit either B or C and then D. So the first one is A. So next I'm going to visit B here. Then after that level by level C and then D. So the level by level visiting of all the nodes will be treated as BFS here. So breadth first search. So in this breadth first search, so what I'm going to say that is, so first we have to be visit to all these nodes which are present in first level. So once this one is completed, then I have to go for the B as the first one, and again I have to visit what are the nodes that are present in this next level. So for the B, so E, and then next one is F, right? So similarly, if I'm going to see for there is no edges here, no vertices are connected, so I have to skip this, and next time I'm going to consider D. So for D, what I have to do, I have to be G here, so that one I have to visit it. Similarly, next I have to see E. So what are the edges that are connected here? No edge, no vertices are there for E, and for F there is only one, that should be H. So this should be the BFS order of this given graph. So see this one. So I'm actually taking a cube here. So in this cube, so how we are going to store the elements? So first one is A. So after that, so what is the first one? B. So I have to first mark down B, C, D first. Okay. So once the all I visited all these nodes at the first level, then how to go for the next level elements. So for the B, what are the for the B, what are the elements? E and F, right? For C there is nothing, and for D the elements will be G. And similarly for E there should not be no elements, and for F I'm going to have H and G for this. So this should be the order of this BFS. So first I have to visit the root node. So from this first vertex, so what are the vertices that are adjacent to A, I have to visit in level by level. So B, C, D, and from this B, C, D once visited, we have to go for the next level. So what are the vertices that are connected to B, E, and then F? So then see there is no vertex is connected. For D, G is connected, so G. So once this one is completed, I have to go for the next level. So for F, I have only one, H. So this should be the first order of this given graph. And next one is that depth first search. So the idea is simple: follow the single path to its end, then backtracking it. So that is the concept in DFS. So this is the algorithm mainly for traversing and searching a tree and tree structure or a graph as well. So once we have started the route, so selecting some one node as the route in the given graph case, and explore as far as possible along the each edge, so before backtracking. So the main idea behind this DFS is that backtracking. So this is the algorithm for traversing and searching a tree, and tree structure or graph is here. So example we have to see. So for this given graph, I have to find what should be the DFS order of this. So for this DFS order, so first I have to visit the root node. So that should be the starting vertex I am going to construct. So this should be the starting vertex. So in this starting vertex, I have to next visit B. So B is the adjacent. For B, again how to check it out what is the adjacent of B. So E I am going to consider. So once this one is ended, I have to go backtrack it, and again how to visit F. For the F, again I have to what is the adjacent one, H. So there is no connections here. So I have to do backtracking up to A. So for A, so again I have to come back to A, and then what is the adjacent that is connected to A, C. So C have to be visited. So there is no adjacent nodes. So again I have to go back to A, and then again I have to visit D, and next one is G. So like this we have to be visit level by level of the nodes here. Okay. So here in the given graph, so what is the first? So the first, this is the starting node. So in this starting node, what I'm going to say, so I have to visit B. So from B, so I have to visit the next one, E. So since this one is ending, so again I have to go back to the starting backtracking, and I have to visit F. From F, from G, sorry, from H to H, right? So again this should be ending. So again I have to go back to the backtracking to the previous node and visit the next one, C here. So again I have to go backtracking, and again I have to visit D, and then G. So this is the way of finding the DFS of this graph. So first A, B is the next, that is adjacent, and B is again, E is the adjacent to B. And again I have to go back and backtracking, and then next adjacent node is F and H. So next one C, again I have to backtrack it and again visit the next one D and then G. So when it comes to the time complexity of this graph search techniques, so the time complexity for the both cases will be big O estimate of V plus E, so which should be implemented using adjacency list, where V should be the number of vertices in the graph and E should be the number of edges. And space complexity, if I'm going to consider, so the space complexity should be big O estimate of V. So since at the worst case we need to find, we need to hold all the vertices in the queue. So DFS space complexity depends on the implementation, a recursive implementation of that. We can have a big estimate of space complexity, that should be worst case, where H should be the maximum depth of the tree, and the depth first search can waste time. So going down a rabbit hole, which when the solution is high in the case of tree, and worst case of DFS will be the best case of this BFS, and the best case for BFS will not be worst case of for BFS. So hence I conclude this. So graph is a nonlinear data structure which consists of vertices and nodes connected by edges or arcs, where edges may be directed or indirected. And the graph can be represented in two ways. So first thing is adjacency list, and second one is adjacency matrix. And graph traversal is a process of checking or updating an each vertex in the graph. So the graph traversal can visit each and exactly one node here. So there are two types of graph traversals, like breadth first search and depth first search. So breadth first search means we have to visit the neighbor vertices before visiting the child vertex, and depth first search is used for traversing the finite graph. Okay, so in breadth first search we have to visit all the childs at level by level, whereas depth first search we have to visit only one node at the each level. That should be the depth first search. So that should be about the graphs here. So here in this video I discussed what should be the graph and what are different types of graphs. So how the graphs are represented here. So the graph is a nonlinear data structure which is connected by vertices and edges, and the representation of the graph should be adjacency matrix and adjacency list. And this adjacency matrix should be a 2 by 2 matrix representation. So for this it should be the space inefficient in case of this undirected graph, and memory usage is big O estimate of n square. Whereas the advantages of this should be easy to understand, implement, and convenient to work, and we can able to remove the edges uh, it's very easily with the time complexity of 1, whereas disadvantages, it should be consumes more space, big estimate of n square, and if the number of nodes in the graph may change, uh, it should be too inflexible to it. Adjacency list should be consists of very easy to implement. So each vertex of the graph contain the list of adjacent vertices and should have very less space complexity, and it should also be allows to store the graph in more compact form, which should be the big benefit for the many algorithms. And disadvantage is that, so it should the time complexity, it should be big estimate of n, since there is an edge from one vertex to another vertex, and should be also the to make an efficient implementation, the dynamic changes of vertex number is required here. And there are different types of graphs like undirected graph, weighted graph, directed graph. And undirected graph means that the way the edges does not have any other kind of edges, the arrows. And in directed graph the edges is going to maintain the arrows in which direction it is. And weighted graph means where the edges is going to hold the weights here. And two types of graph traversal, like to breadth first search and depth first search. So for both the cases, first we have to visit the one node. From that node you have to be put the childrens of that node into either in stacks or queue. For each child we have to be perform search operation. In order to implement this depth first search, we have to be use the data structure stack, and in order to implement breadth first search, we have to implement the data structure queue. So in breadth-first search, we have to visit all the childrens before the grandchild, and the weakness is that we need more flags and to prevent the infinite loops. So this is algorithm for that, and this is the problem. So in this problem, I have to visit all the nodes in level by level, and in depth first hash, which is the algorithm mainly for traversing or searching a tree. So once we started at the root and explore, we have to be more possible before backtracking. So example of the first. So we have to visit level by level of each node, and you have to again come back and perform the backtracking, and you have to visit. And time complexity and space complexity should be same in both the cases. And this is the conclusion of this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.